one of the things that you will find out as we progress through this course is that a lot of times we're going to need to guess the solutions to our differential equations. It's actually the method that we're going to use to find solutions to differential equations is to guess. And then we're going to have to verify whether those guesses are actually the solutions to the differential equation. This is a technique that you have done before. A lot of times, probably earlier in your math career, okay, you wanted to do the integral of x squared dx. And so you had to find the antiderivative. So you kind of had to guess. And so initially you're thinking, okay, x squared, the power rule, so that must come from x cubed. Okay, so because the derivative of x cubed is a multiple of x squared. Okay, but if we took the derivative of x cubed, we'd get 3x squared, and so we'd have 3 too many. So instead, maybe we're going to write this, we're going to adjust our guess. We're going to write 1/3 x cubed, okay, because 1/3 x cubed, if we take the derivative, will actually give us x squared. So we guessed something, x cubed, and then we adjusted our guess and put the 1/3 out front, okay, and that gives us an antiderivative. We probably have to adjust our guess again and add a plus c just in case for that arbitrary constant. So guessing and checking is kind of our method for finding antiderivatives. Well, the same is going to be true for differential equations. And so the first thing that you need to learn is that if you have a solution to a differential equation, can you verify that it actually is the solution? Okay, can you make that substitution? Okay, so I'm going to have 3 problems here where I've given you the differential equation dy dt. In this case, this first one is dy dt is 2y minus 5. And then I gave you the answer. How kind of me. I gave you the answer. And all I'm asking you to do is to verify that it is the answer. So to verify that this is actually the answer, you're going to need to find the derivative, dy dt. Find what that is. And then you need to tell me what 2y minus 5 is, what's on the right-hand side. And if those two expressions are equal, then you have verified the solution to the differential equation. So I want you to take a second and see if you can do that for A, B, and C. Can you find the appropriate derivative and then substitute in the function to the right-hand side and show that those things are equal? So take a moment to do that and pause this video. And now I'll assume that you've done that you've taken a moment to pause this video. And so we will go over these answers now, okay? So I want to find dy dt, given that y is 3e to the 2t plus 5 halves. So dy dt in this case is just 6e to the 2t. And so I've found what the left-hand side of the differential equation is. I want to now know what the right-hand side is, 2y minus 5. So that's 2 times 3e to the 2t plus 5 halves. And then I'm going to subtract 5. Okay, so I'm going to multiply out the 2. So I'm going to get 6e to the 2t. And then I'm going to add 5 and subtract 5. Okay, because 2 times 5 halves is 5. And then, of course, the minus 5 is still there. Okay, so if I add 5 and subtract 5, what I'm left with is just 6e to the 2t. Aha. So the derivative is 6e to the 2t. The right-hand side is 6e to the 2t. And so I've verified that this is the solution to the differential equation. Let's try another one. This one's a second-order differential equation. D squared x dt squared is minus x. So notice that in this case, x is actually the function, x of t. Okay, x is not the variable, but it's actually the function. Okay, so x of t, I'm going to tell you it's sine t. Well, how do we know that that's true? Well, let's find dx dt. The derivative of sine t is cosine t. But I need to know what the second derivative is. So d squared x dt squared. So the derivative of cosine t is minus sine t. And hopefully at this point you can recognize minus sine t is really minus x, because x is sine t. And so I've shown that the second derivative of x with respect to t is actually just minus x. So I, yes, again, have verified that that is the solution, or a solution, as we'll find out later. Okay, let's do dz dt is minus t times z. Eventually, we're going to learn how to solve this equation, and we'll find out that the solution is e to the minus t squared over 2. Okay, so let's take the derivative and see if that makes sense. So the derivative dz dt is going to be e to the minus t squared over 2. It's itself times the derivative of what's on the inside here, minus t squared over 2. So that's going to be minus t. So I'm going to write this as minus t e to the minus t squared over 2. Oh, well, that's minus t times e to the minus t squared over 2. Well, that's z, okay? And so it's minus t times z. So we again have shown that e to the minus t squared over 2 is a solution to the differential equation. I want to finish up this video by talking about something that's really important for analyzing differential equations, and that's what's called a slope field. A slope field is a plot of the slopes of the tangent lines to the solution of the differential equation. That's called a slope field. So what you see in this graph is a graph of a bunch of slopes. This is for the differential equation dy dt equals 0.1 y times 20 minus y. And so what's happening is that at every point, so we can pick a point. We could pick the point, say 6, 10, right there. We could pick that point. At that point, there's going to be a slope. How do you find that slope? Well, you plug in that point 6, 10, to the right-hand side of the differential equation. Okay, so it's going to be 0.1 times y, which is 10, times 20 minus 10. Okay, 0.1 times 10 is 1, and 20 minus 10 is 10. Okay, and so at that point, we know that the derivative is 10. So therefore, the slope here of this arrow, okay, the slope here is equal to 10. And if you do that for every point in this ty plane, you create a slope field. And then these slopes are telling you the slopes of the solution to the differential equation. So that if you start at a point, let's start at that point 0, 1, essentially what you can do is you can follow the arrows because they're pointing in the direction of the rate of change. You can follow these arrows, and that gives you a rough sketch of the solution to the differential equation. And so these slope fields are helpful for understanding kind of the general paths that the solutions to the differential equations take. There are going to be some special solutions that we're going to want to look at. They're called equilibria. An equilibrium solution is going to be a solution that represents no change. That's, of course, where the derivative is 0. If there's no change, then the derivative is 0. So for the differential equation, dy dt equals 0.1 y times 20 minus y, there are actually two places where this derivative is 0. If y is 0, the derivative is 0. And if y is 20, the derivative is 0. And you'll notice along 0, the arrows point horizontally. Okay, so a solution is just going to move along horizontally because there's no change. So if you start at 0, you remain at 0. And then if you start at 20, you get the same thing where the arrows are pointing horizontally. So if you start at 20, it remains at 20. Okay, so these are slope fields. Now you can explore all sorts of different kinds of slope fields, okay, using an app. I'm going to show you an app called Slopes. Slopes is an app that's currently available for the iPhone and the iPad. But if you want to look at slope fields for a differential equation, here's a differential equation, y prime equals ay plus b, where a is negative 0.5 and b is 2.5. Then you see a bunch of arrows laid out, okay? And they give you the general trajectories of the solution to the differential equation. They tell you what the slopes are, okay? So if you start at some point, let's start at the point 0,1, and I tap on the screen at the point 0,1, then you see that the solution follows those arrows. And so you can tap on another initial point and you can see it follow an arrow. Okay, so this tool will be helpful in plotting slope fields and kind of understanding the general trajectories of these solutions to the differential equation. Okay, so let's look at the consequence of some of these slope fields, okay, and what you can discover from these slope fields, and that is families of solutions. Okay, so a differential equation isn't going to just have one solution, it's going to have a family of solutions. And that's because each one of the solutions will correspond to a different initial condition. So each one of the solutions that you see in some of these graphs that I have for you, they correspond to a different initial condition, but it's the same differential equation. So I have some examples of some differential equations like the ones that you see below, and each one of them has a slope field, okay, and depending on where you start, where your initial condition is, you're going to get a different curve for a different solution. And so these form families of solutions. So as we progress through the course this week, we will be graphing a lot of differential equations, graphing the slope fields of these differential equations, and then looking at the trajectories of the solutions, these families of solutions. Well, that was our introduction to differential equations, and I look forward to exploring some more activities about differential equations with you during the rest of the week.